Hello, in this video, we're going to take a look at 3 examples of using the limit comparison test. So first thing first, when using the limit comparison test, we want to make sure our series has positive terms. So we're looking at this sequence, n to the fourth over plus 1 all under a square root plus n cubed plus n squared. Since everything we're plugging in is positive and we're only adding and using exponents, this, of course, is greater than 0 for our positive greater than 1 inputs. So yes, this is positive. Now we want to find what to compare to. Now we're going to compare to some series, n equals 1 to infinity, and finding the series to compare to is to look at the big things happening. In the numerator, this plus 1 isn't doing a whole lot. So I'm going to ignore that and say, okay, my numerator is really just the square root of n to the fourth. Well, the square root of n to the fourth is n squared. So we're going to use n squared in that numerator. And the biggest thing in the denominator, there's a fair amount going on, but the biggest thing is the n cubed. So we have n squared over n cubed. This is also the series n equals 1 to infinity, 1 over n. Step 3 is to determine, does that series converge or diverge? And this diverges because it is the harmonic. That is the p series when p equals 1. We're comparing to 1 over n. The limit comparison test tells us to take the limit of our sequence an over our sequence bn. 1 over n. bn, an. Keep change flip gives us the limit as n goes to infinity of n times the square root of n to the fourth plus 1 all over n cubed plus n squared. We can use the trick of dividing by the biggest thing in the denominator, but also in general, if we look at the degrees here, the degree of the numerator is generally an n cubed because we're looking at the square root of n to the fourth times n. So we have an n cubed. And in the denominator, we have an n cubed. So n cubed over n cubed, their coefficients are 1. This is 1 over 1 or 1. So the limit is 1 and 1 is positive and finite, which means the series we're looking at, the n to the fourth plus 1 square root all over n cubed plus n squared, does the same thing as the harmonic series. This means that the series n equals 1 to infinity of the square root of n to the fourth plus 1 all over n cubed plus n squared diverges by the limit comparison test, since the harmonic n equals 1 to infinity of 1 over n diverges. Some things we need to see in the work is our conclusion sentence of our series converges or diverges by the test with our reason. But then inside of the work, we do need to see that our limit is between 0 and infinity. And we need to see the work of the limit. And basically what we're comparing to. And why does it diverge or converge? Basically, this here is showing essentially the minimum amount of work that needs to be shown on a problem like this with everything lined out exactly. But our conclusion sentence is just series converges or diverges by the test with a reason. All right, so next example. The series n equals 1 to infinity of n plus 8 to the n over n plus 9 to the n. So far, we've only been comparing to p series, but this is a case where we're going to compare to a geometric series. But before we do that, is this positive? Yes, it is. It's greater than 0 for n greater than or equal to 1. This is true. There is nothing there that is ever negative to cause any issues. So now we are going to find what to compare to. And it's following the same order of we want to compare to the series that has the biggest things happening. So the biggest thing from the numerator is this 8 to the n. And the biggest thing from the denominator is the 9 to the n. So we have 8 to the n over 9 to the n. We have a fraction where both the numerator and denominator are being raised to the n. So we're looking at the series n equals 1 to infinity of 8/9 to the n. This converges by the geometric series test, because this is a geometric series, with the absolute value of r, which is equal to 8/9, which is less than 1. So there are the first 3 steps on the page. Step 4 is to run the test. Limit n goes to infinity of n plus 8 to the n over n plus 9 to the n, all over 8 to the n over 9 to the n. Keep change flip. N plus 8 to the n over n plus 9 to the n times 9 to the n over 8 to the n. Multiplying everything in, we have 9 to the n times n plus 8 to the n, or 72 to the n, 8 times 9. All over 8 to the n times n plus 72 to the n. The idea of limits where we can divide by the biggest thing in the denominator. The biggest thing is that 72 to the n. So limit n goes to infinity of 9n over 72 to the n. 72 to the n over 72 to the n. 8 to the n times n over 72 to the n plus 72 to the n over 72 to the n. Growth rates tell us this is 0. And so is this. This is 1, and this is 1. So we have 1 plus 1, or 1 over 1. 1 over 1, which is 1. And 1 is between 0 and infinity. So that means this series does the same thing as what we compared it to. So what we compared it to converged, meaning the series n plus 8 to the n over n plus 9 to the n from n equals 1 to infinity converges by the limit comparison test with, or since, the series n equals 1 to infinity of 8/9 to the n converges. Okay, so there is that example. And now we have one more. We have this series n equals 2 to infinity of 1 over the natural log of n. First thing first is this positive 1 over the natural log of n Is this greater than 0? Yes. The natural log of n is only negative for values smaller than 1 or between 0 and 1. Since we're starting at 2, we have thrown out all the negative. And since we're starting at 2, we also don't have a problem of dividing by 0. If n was 1, we would be dividing by 0. We'd have a problem. So we've thrown out all the negatives and we have thrown out our undefined location. So since we're looking at n greater than or equal to 2, yes, this is positive. So now we can find what we want to compare to. We want to compare to some series that is like 1 over the natural log of n. A series that is like 1 over the natural log of n would be, we squint a little, 1 over n. Because we're looking for a p series we know about. And the natural log of n isn't staying fixed, it is growing. So I can't just replace the natural log of n with a number here, like we did in a direct comparison test. We were able to do that in a direct comparison test because it made our fraction order what we needed it to be. But in this case, natural log of n is doing something, so we need to keep a variable there. But we want to compare it to a p series. The simplest p series that's the same is 1 over n. We've already identified if this converges or diverges many times. This diverges because it's the harmonic. Now, we run the test, the limit as n goes to infinity of what we're wanting to know about divided by what we already know about. 1 over the natural log of n divided by 1 over n. This is equal to the limit as n goes to infinity of n over the natural log of n, which equals infinity by growth rates. Infinity is not 0, and infinity is not finite. Or, sorry, infinity is positive, but it's not finite. Not 0, it's not a finite number. But in this case, it is positive. We didn't get negative infinity. However, it's not the case we want. We want 0 less than c is less than infinity. We want a positive finite number. However, since we got infinity, what we want to do is go check, is this one of our special cases? I'm going to go up to our special cases. Our special cases say that, zooming out, if we get a limit of 0 and the series we're comparing to converges, then the series we want to know about converges. If we get a limit of infinity and the series we're converging to diverges, then it's divergent. We got a limit of infinity, so we're checking this one. And we were comparing to 1 over n, which diverged. So we have actually all the properties here of our special case. We have a limit of infinity and a comparison series that's diverging. So since we have both the properties we want, we can still make a conclusion. If, say, this was, we compare it to n squared. And if we compared to n squared, or 1 over n squared, we compared to 1 over n squared, we would have actually gotten the same limit. We'd have n squared over the natural log of n, which is still infinity. However, 1 over n squared converges, and so that wouldn't have actually worked. But because we're comparing to something that diverges, and we get the limit of infinity, since both those things are true, we can make our conclusion. So the series n equals 2 to infinity of 1 over the natural log of n, because our limit's infinity and 1 over n series diverges, this series diverges as well by the limit comparison test. I'm going to put both those pieces in the conclusion sentence, make it clear. Both of these were necessary. And 0 less than c is less than or equal to infinity, because c is infinity. To be clear, this line is important in all the limit comparison tests to say this is what my limit came out to be, and it is positive and finite, or it is not 0 and it's not infinity, or in this case, it is infinity and we have our special case. That line is always important, and I'm including it in the sentence here to add on to its importance of the fact we got infinity. So there are 3 examples of using the limit comparison test. And so now we have our 2 comparison tests that can be used for telling if a series converges or diverges.